Hello, AP Calculus students. Mr. Ford here with another homework tutorial. This is 6.1.1. We'll be doing problems 6-9 all the way through 616, and you might be surprised at the amount of Algebra 2 review there is inside of this assignment. So let's jump into it. Speaking of Algebra 2 review, maybe pre-calc review, let's remind ourselves for a second how logarithms and exponential equations work. So all we have here is a 2 to the x power, and all I want you to remember is there's kind of this number shuffle that goes on. If you have an exponential agreement, like y equals b to the x power, some base there, you can think about this. Its inverse would be the log base b of x equals y. This is in many ways a number shuffle. The base is the b, and that's the base in both cases. Of course, what's really going on here is you're asking yourself, if you're in an exponential world, let's say you're counting by, I don't know, multiplying by 2. And maybe this diagram is a little bit too advanced for the scope of this video, but it's worth mentioning. In this world, you're multiplying by 2 each time to get to the next step, times 2, times 2, times 2, times 2. What we've got here is we've got a system that counts by times 2. And that's why we call this a logarithm of a base of 2, or an exponent, 2 to the x power. There are kind of two questions to ask here. If I go, for example, 3 steps, 3 being the number of steps that I take, I'm going to land at 8, and that's the end of the problem. If we count by multiplying 2's and we take 3 steps, we'll land at 8. A logarithm asks the opposite question. It says that, okay, if I'm counting by 2's, how many steps does it take to get to 8? So again, now you get the end here in mind, but what we want to know is the number of steps. These two are inverses of each other. They both agree that we're counting by multiplying by 2, but they're asking different questions. The first one asks, hey, I'm taking 3 steps, where will I land? The second one, the logarithm, asks, I want to land at 8, how many steps do I have to take? That's the idea. Now with that crash course out of the way, this is actually really simple. All we got to do here, this is the inverse, f inverse of x, is just the log base 2 of x. That's all you have to do there. All we're doing is thinking about it as a logarithm instead. And then for question B, the f inverse of x in this case would just be 3 to the x power. That's all you need to do. Here you have the log base e of x. The inverse there, of course, is the e to the x power, which we'll talk about tomorrow in class. And here you have 5 times what's going on here. There are a lot of ways to think about what's about to happen here. If you want to write this as a logarithm, let's see. What you would have is we got to think about this inversely. If you want to, let's see. Maybe it might help in this problem to think about it as a y equals. Y is 5 times 9 to the x power. And maybe in this case, we would switch the order around. This is typically how we handle inverse problems. We switch the order. We say x equals 5 times 9 to the y power, like that. The only reason why I'm really writing this out is to explain why the first thing I would do here is divide by 5 on both sides. And that gives us this step, x equals 5, or x over 5, is equal to 9 to the y power. And at this stage, you can just take the logarithm of both sides and get it there. At this point, y is equal to the log base 9 of x over 5. It's a little more advanced than we need to get for this review question. The first 3 are all that really matters. We're going to be talking about a lot of inverses and logarithms and exponential equations here in Chapter 6, so we're getting that in the forefront of our mind. Let's move on. 610 is going to ask us to do kind of the same thing here. It does give us a process to work with. That gives us an example here. We're going to rewrite the following equations using powers of the specified base, and an example is shown at right. So let's follow this example for part A and see how far we can get. All we're going to do is we're going to take the log base 5 of both sides. Log base 5 of y will equal the log base 5 of 3 to the x power. Now what's going to happen here is that, let's see, what happens next? Trying to understand what the next step was. Oh, kind of the invisible step here. I'm looking at this example that we did here. Over here in this step, the way I think about what's about to happen is you'll take 2 and raise it to the power of both sides. The reason why, you'll notice that you have log base 2 of y and x log base 2 of 5 right there. The reason why that works, well, first of all, you have 2 raised to both that power. But what's happening here is that 2 raised to the log base 2 power, or log base 2, those are going to cancel out, leaving just the y by itself. Y is equal to 2 to the x log base 2 of 5 power. So if we use that same kind of logic over here in this example, the first thing I'll actually want to do is a substep that we didn't do in the previous example. This exponent of x is going to kick down into the main line and multiply in front, x times the log base 5 of 3. And now what we're going to do, I'll write this step out in this example, and then we'll kind of just meld it out into the next few problems. We're going to take a base of 3 and raise both sides power. I don't know how to say this. I've always struggled with how to say what's going on here. We're going to raise 3 to the power of both sides there. Or, sorry, not 3 in this problem, 5. What am I doing here? Because we want the 5 to the log base 5 to cancel out over here on this side, leaving y equals 5 to the x log base 5 of 3. Right there. That would be kind of the final answer there. Now, you might be able to follow that pattern right now and actually just fill in the blanks for the next problem. Like, for example, if you're just following the structure going on there, question B, the answer is going to be y equals, let's just try to think about this here. The last time, base 5 ended up being the bottom, so let's make 10 the bottom this time. Then we had x in every case. And we're going to have a log base 7. That's the base of the logarithm there. So log base 7 of... Am I thinking about this the right way, or am I going to get stuck in my own brain here? Hang on, processing. I guess it's a log base 10, isn't it? It's a log base 10, yeah, of 7. That's what's going to go in there. Log base 10 of 7. That number, yes, okay, I guess I mishighlighted. The number 7 is going to end up inside the logarithm because that's where 3 ended up last time. All right, base 5 was right there also. Okay. That makes sense. The only thing about question B is that we would never write log base 10. Log base 10 is known as what's called common log. So x log of 7 is all you need to write there. For question C, if we follow the exact same pattern, we're going to have y equals... Let's see, we start with the base of e raised to the x log base e of 2. And again, log base e has a special name too. It's called the natural log of 2. There we go. So we're getting logarithms and exponentials kind of in the forefront of our brain here as we continue to think about other things too. Also, things we need to be pushing forward with a little bit, proportional relationships, which are really simple. Given parts A through D below, all we're going to do is decide if these are proportional relationships or not. And if so, we're going to write an example of why they're proportional. Now, an example is given for us again. The distance traveled in miles when driving for t hours at a speed of 50 miles per hour. Well, in that case, you can write it as a really simple d equals 50 times t. There you go. When you're talking about proportional relationships, basically the question is, can you write it as y equals k times x? That's a proportional relationship. Is there just something that you're multiplying by every time? So for example, question A, cost C in dollars of N chocolate bars sold for 50 cents each. Well, the cost is just going to be 0.5 N. That's it. That's a proportional relationship. In this case, the constant is 0.5. That's all we're doing here. Question B, the number of hours it will take to drive 50 miles at R rates per hour. Now this seems proportional, but the trick here is that we do not know what the actual rate is in this case. It's not going to be proportional because we don't know what the variable is. If you want to think about distance equals rate times time, in this case we want to know the time. And if you solve for the time in this case, the time is actually equal to the distance divided by the rate. And since we're talking about division here, this is not proportional. It's the division that's going to make it happen there. We're looking for a relationship that multiplies, not divide. Let's look at C. Taxi fare F for M miles driven. The fare is $2 for the first mile, then 1 for each subsequent mile. The problem here is that the fare is changing. It's $2 for the first, and then $1 for each subsequent mile. I mean, this is a pretty reasonable thing to write down in like an Algebra 1 class. The fare is, I don't know, it's 2 plus 1 times x minus 1, maybe something like that. But the problem here is that this is a linear equation. It's the y-intercept that does it. The y-intercept makes this not proportional. Proportional equations only have the multiplier, no plus at all on there. Question D, the time t it takes to read n mystery books if each book takes 10 hours to read. This is a great proportional problem. T is equal to 10 times n. In this case, the constant is 10. Really straightforward. Don't think about it too much. Question 612. Now we got a bunch of integrals to evaluate, and we are to consider the multiple tools available for integrating all of these things and use the best strategy. Now question A is a definite integral, and it's a pretty easy antiderivative. We've seen it a few times actually in a warm-up and also on the test recently. This is just the tangent of x. But it's a tangent of x evaluated from pi over 3 to 0. So you kind of have to bust out your trig knowledge. Maybe we should do this off to the side there, because I always need to think about tangent a little closely. We're looking for the tangent of pi over 3 minus the tangent of 0. Essentially what's going on here. For the pi over 3, if I think about this for a minute, here's my unit circle. Pi over 3 is the taller of the angles there. In this case, the tangent is going to be the square root of 3 over 2 divided by 1/2. And the way I like to think about this is the 1/2's actually canceling out. So get you the square root of 3 over 1. So I know this is the square root of 3 minus 0, and so it's the square root of 3. It's kind of my logic for this problem over there. So when you're evaluating this integral, it's going to end up being the square root of 3 right there. For the next one, this is a indefinite integral, so we will not be actually getting a number answer, but we do have to kind of take the antiderivative. The antiderivative of secant tangent, that's just the secant. And the secant of y, I guess, in this case. The derivative of secant is secant tangent, so there's an antiderivative relationship there. For the next part of it, let's keep the minus for now. We need y to go to the 5/2 power. Now, the way I like to do these problems is I want to leave that 5 that we have right there. I want to leave it there, but I want to multiply y by 2 over 5. The reason why is I want to kind of set up right now how it's got to cancel out. When you bring the 5/2 down, it will cancel out with the 2/5 that I just put down there. And then the 5, we need that to remain because that's in the original problem over here. So if we simplify this a little bit, it'll be the secant of y minus 10. Oh, actually, the 5's actually cancel out. So it'll be minus 2y to the 5/2 power plus c. Don't forget your plus c on that one. Pretty groovy. The next question, we do not have a way right now to evaluate arc sine. We will later on in this class, but right now the calculator is the only method that we have for this problem. So let's first of all make sure we're in radians mode for this class, and we will go open up our calculator and open up fn int. We're going to go from 0 to pi over 4, and we are just going to do the inverse sine of x dx. It's going to be about 0.3284, and that's all we're really going to do for this problem. It's approximately 0.3284. It's all you really have, the only tool we have of doing this one right now. And question D, this is another one that, it might be helpful to expand it out first before we actually find the antiderivative. So you're going to have t to the 4th. You're going to have 2 instances of 3 times t squared. So let's call that 6t squared plus 9. That's the antiderivative of, or that's at least the expansion part there. And now we'll just take the antiderivative. We need t to the 5th power over 5. We'll cancel that out. Next, we're going to have 6 times t to the 3rd power over 3, and we'll let the 6 and the 3 balance out there, plus 9t plus c. The only edit we need to make to this in our final step is to divide the 6 by the 2. So how about t to the 5th over 5 minus 2t to the 3rd plus 9t plus c. Don't forget your plus c there. Going to the next page, we got a bunch of limit problems in 613. The first one is actually really simple if you look at it. We're taking the limit to the limit as x approaches infinity of this insane polynomial. But when it comes to insane polynomials, the only thing we care about if they're being sent to infinity is the leading term. The only thing that matters is the biggest term there. We have x to the fifth on top, x to the third on bottom. So what's going to happen here is both of these are going to go to infinity because x to the fifth and x to the third both go to infinity if you plug in big numbers to them. But the number on top will be faster. It's kind of hard to describe it. It's a bigger infinity than the one on bottom. So the overall limit is going to go to infinity, which therefore means it does not exist. This limit goes up forever. Question B is exactly the same question. The only difference now is we're plugging in negative infinity. So what's going to happen here is we are going to think about the same exact thing. X to the fifth and x to the third is the only thing that really matters here. Everything else gets dwarfed as you plug in huge numbers. Even x to the third doesn't matter when compared to x to the fifth, for example. But when we're comparing x to the fifth to x to the third, now this time we're going to have negative infinity over negative infinity. And again, the one on the bottom is going to go faster than the one on the top, and the negatives are going to cancel out. So you're still going to positive infinity, and therefore this limit does not exist. You could try graphing this in Desmos if you want to. I would not recommend this, but you'll see it happen. Question C, here's where we're going to get something a little more tricky. The first thing we should try on question C is try plugging in 0. If you do that, you'll pretty quickly realize that you get 0 on both the top and the bottom. Well, do you get it on the top? You do. You do get this on the top. So what we're going to do here, wow, this problem sucks. You know what? I do not assign this problem. Question C is out. Here's what you'd have to do. You would have to use L'Hopital's rule. You would have the limit as x approaches 0 of 2 times the cosine of 2x for the chain rule minus 16x. And that would all be over, you got to use the product rule down here. This is 4x times derivative of the second part, which is times 3 times x minus 10 to the second power times 1 plus the new derivative derivative of the first times the original second. Right there. Now, technically, that's done because you no longer get 0 if you plug 0 into both of these things. If you plug 0 in now, this becomes 1. This becomes 0. So this is 0 here. This is now 1. 2 times 1, sorry. This whole term becomes 0. But this number here, if you plug 0 in right there, that's negative 10. So what you end up with is you get 2 on top. And on the bottom, you get whatever 4 times negative 10 to the third power is. So that is 2 over negative 4,000, which is negative 1 over 1,000, negative 1 over 2,000. So I guess it's not so terrible, but that's kind of a dumb problem. You can make a much better problem out of that. So, C, do it if you want to. You don't have to. Question D, I suspect is going to be very similar. Right away, I noticed that if I plug in 2 on the top, you get 0. So this is 8 times 0 squared on the top. On the bottom, you get 4 minus 10 plus 6, which is also 0. So because we get 0 over 0, we can say that L'Hopital's rule applies, which is a good thing to write down to your AP exam reader so that they know what you're doing. Now we're going to look at the limit as x approaches 2 of the derivative of this. And this is not as nice or any better of a problem as the previous one, but at least it's something. On the top, the derivative is going to be 16 times x minus 2, which is still 0 if you plug it in. And on the bottom, you get 2x minus 5, which is not 0 if you plug in 2. So at this stage, if you plug in 0 now, you get 16 times 0 on top. You get 4 minus 5, negative 1 on bottom. That's 0 over negative 1, and so the limit is 0 overall. The next question, question 614. If f is an even function and f prime of 0 exists, what must f prime of 0 equal? Well, the thing about even functions is that they are symmetric to the y-axis. So, and if f prime of 0 exists, what must f prime of 0 equal? The only way you could be symmetric to the y-axis at 0 is if you have a horizontal tangent. Because if you think about this, if you try to draw an example of this, any graph that's symmetric to the y-axis has to level off right there so it can be reflected over here. So you've got to have a horizontal tangent no matter what, right there. So f prime of 0 must equal 0 in any even function. It's kind of a cool observation. Not a very important problem, but hey, you know, an observation nonetheless. 615, sketch a continuous function with the following properties. F prime of negative 2 equals 0. That's going to give us a horizontal tangent. F prime of 3 does not exist, so we can have a sharp corner there. Or an asymptote. That would be an option too. And f double prime of x is less than 0 for x equals 3, so it's got to be concave down, CC down. And f double prime of x is greater than 0 for x is greater than 3, so that's got to be concave up. So let's think about this for a moment. We're just trying our best to sketch a graph right in this little space right there. How about that? So at x equals negative 2, we have to have a horizontal tangent. Let's put a point anywhere. It doesn't really matter where it is. F prime of 3 does not exist. 1, 2, 3. Negative 2. So let's think about this. And we need a graph that is concave down on the entire range from 0 to 3. Concave down all the way through. So it's got to be concave down the entire time. So how about we have a graph that comes up like this, makes our horizontal tangent right there, and continues to be concave down all the way until you hit 3, maybe like that. And then you have a sharp corner. Or how about an asymptote? That would work. Or how about a jump discontinuity? That would work too. Because then you can make a concave up from then on like that. Something like that. That would work. Maybe make an open circle up here so you don't have a non-function thing happening. Pretty cool. And the last problem, locate the point of inflection on the graph of f of x equals 1/3. So f prime of x would be 1/3 times x to the negative 2/3 power. And f double prime, which is where we find points of inflection, would be negative 2 over 9 times x to the negative 5/3 power. So what we need to do, if we're looking for a point of inflection, we need to figure out when this thing equals 0. That's what we're looking for. So let's consider this. We have, if we clean it up a little bit, 0 or does not exist. Let's think about that for a minute too. That might be a thing we have to think about. Because if you rewrite this problem, what you get is negative 2 on top, 9 on bottom, and the third root of x to the 5th on the bottom also. We want to know when this either equals 0 or does not exist. I think it's pretty easy to say that's going to happen when x is 0. Because if x is 0, then the whole function becomes 0. And I think that's got to be it. X equals 0 has to be the spot right there. I think that's got to be the point of inflection. Yeah. And of course, the point itself, if you take x equals 0 and plug it back up into the original function, 0, or sorry, whoops, that's the derivative up here. 0 to the 1/3 power is also 0. F of 0 equals 0. So the actual point would be at 0, 0. That's a pretty easy question to answer. Okay. Pretty cool one. Got one in the tank ahead of the game. You guys are doing great. Keep it up. Don't let those logarithms fool you. They're actually very simple, especially for this class. So I'll see you in the next video. You guys are awesome.